Okay, in the last session, we had seen the correlation between H parameter model to hybrid pi model at low frequencies, and at high frequencies this is accurate and this is not accurate. That is the limitation of H parameter model. And we have correlated H parameters to GM. Now let's see what is GM from the definition, and I'll give you the derivation part. Right, with that this is over. Let me arrange everything. Now GM, right? Therefore, this is what is GM. BJT, the transconductance, GM from hybrid pi model. Okay. What is the definition of GM? GM is nothing but definition. GM is defined as, what is the name? GM, transconductance, right? Therefore, if you take your BJT, right? This is what is your BJT, right? Now this is what is your base, emitter, collector. Okay. Now this is what is your common, and this is what is our VCE. This is our VCE. I'm taking like DC, and this is what is our VBE. Okay, and this is what is your IB, and this is IC, capital IC. Okay, you will understand why I'm taking now DC, right? Because DC also you can consider, but we have to convert into AC parameters, because IC1, IC2, those things we have done already. I'm speaking with respect to the definition, right? What is GM definition? I want to know the change in IC. I want to know the change in IC only because of VBE. I want to know the input voltage, how it is controlling your IC. Therefore, what is that? People use partial differentiation. Delta IC, the change in output current, because of what? Because of VBE only. Because of VBE only. Then what does it mean? Because we know that your IC is controlled by VBE. I agree. But your IC is also controlled by VCE because of base width modulation, right? Your IC is also a function of VCE. If VCE is increasing, your IC is also increasing. That is because of base width modulation. But what I want to know, I want to know change in IC only because of VBE, not because of anything else. You remember, it is something like output impedance, right? While we measure output impedance, what I told? Exclude the load, put output voltage, then because of output voltage, whatever output current you get, that is what is output impedance, output voltage by output current. But we know that when you apply output voltage, when you get output current, that output current is not only because of output voltage, that output current is because of input parameter also. Then we kept the input parameter constant, or we took input voltage constant, which is nothing but R Thevenin. Similarly, I want to know the change in IC because of only VBE, not because of anything else. That is what is called transconductance parameter, transfer from input to output. Therefore, what is the transfer and the relation between VBE to IC? That is nothing but conductance. Therefore, transconductance. Then keeping VCE constant. When you keep VCE constant, how will you keep VCE constant? You apply battery, but don't change it, right? If you don't change it during AC analysis, that is nothing but zero, because that is not changing. Only we are looking for change in quantity. Therefore, then keep VCE constant, put a battery, then change VBE, then you will get IC. Therefore, IC change is only because of VBE, not because of VCE, because keeping VCE constant. Maybe if I change, this is nothing but what? Change in IC, we are representing with what? Small IC. The change in IC, we are representing with small IC. Then change in VBE, we are representing with small VBE. And when I say delta VCE constant, right? What do you mean by delta VCE? VCE constant, then delta VCE is equal to 0, or small VCE is equal to 0. This is what we used before while correlating H parameter model to hybrid pi model. GM, right? When VCE is equal to 0, that time VCE is 0 means small VCE is 0 means there is no change in VCE, no confusion. But normally we will confuse what is the difference between capital VCE and small VCE. Here I am saying capital VCE constant, I am saying small VCE is 0. Capital VCE constant means DC. But what is change in the DC? There is no change in DC, right? If I say DC, there is no change. Therefore, change is 0. You understand the point? That is fine. Now, that is what people say. Maybe for your understanding, the changes on top of DC, you'll have small VBE. The change on top of capital IB, you'll have small IB. On top of capital IC, you'll have small IC. On top of capital VCE, you'll have small VCE. Right? Therefore, what I am saying, small VCE is 0. There is no change in VCE, means VCE constant, capital VCE. Then, but I am changing VBE because VBE is there. There is a small VBE. Because of change in VBE, definitely there is a change in IB. Definitely there is a change in IC. Now, I want to know what is the change in IC, which is nothing but small IC. Because of change in VBE, not because of change in VCE. That's why small VCE is equal to 0. If you want, you can understand in that way also. Anything is fine. Okay. Now, if this is what is the definition, right? Therefore, this is what is the definition of your GM. Remember, it is not only for your BJT, this is true for your MOSFET also. In the case of MOSFET, right? What is this? Maybe I can explain now only, but you can take anything. Therefore, now this is what your MOSFET, let us say. This is gate and this is source, this is drain. Then what is this? This is basically your VDS, capital VDS. And you have capital ID and you have capital VGS, right? Now, what is GM for this? If you ask me what is GM for this, the GM for this is the transconductance is equal to change in ID because of change in VGS, when VDS is constant, or but if there is a change in VGS, let us say small VGS, then definitely there is a change in ID and there is a change in small VDS, but the small VDS is equal to 0, right? That is what, maybe if I write in that way, what is change in ID? Change in ID is small ID. What is change in VGS? Change in VGS is nothing but small VGS. Capital VGS is not changing, that is fixed, DC voltage. Therefore, change in VGS is nothing but small VGS. When, what is change in VDS? I am saying VDS should be constant, there should not be any change. Small VDS is equal to 0. This is from mathematics. Qualitatively, I want to know the change in ID only because of VGS, not because of anything else. That is, what does it mean? Keep output voltage constant, observe the change in output current because of only input voltage. That is what is input parameter to output parameter relation, which is transfer, therefore transconductance. Maybe in future if you get some new device or system, you can calculate GM for system also, which is transconductance gain. If you take a system, black box, what is change in output current because of change in input voltage, keeping output voltage constant, or the change in output voltage 0. That is the definition of transconductance, right? Therefore, this is what is the definition. And remember, this is for your MOSFET. Anyway, this is what I am going to use later. But anyway, just to correlate between BJT to MOSFET, I just explained, irrespective of anything, the definition of GM is nothing but the change in output current because of change in input voltage only. When I say only, means keeping all other voltages constant. That is the meaning of it. Okay. Take it, then we will derive, because we know IC, right? IC is equal to alpha into IE plus ICBO. Then we can use it and we can differentiate and we will get the relation. Okay. Take it. So it is like this. This is for BJT and this is for MOSFET GM. I just explained just to have the correlation between BJT to MOSFET. Okay. Here the small VDS should be 0. Here the small VC should be 0. I'll give 30 seconds to complete. Try to complete it fast. And after that we will derive what is GM. I'll derive GM for this also, but when I start MOSFET, right, I'll explain what is GM, but the definition is this. Similarly, the definition of BJT is that. Now let's derive what is GM. Okay. Now let's see what is GM. Can I erase this? Okay. Now I want to derive, right? Therefore, we know that what is IC? IC is equal to, we already derived, right? Alpha into IE plus ICBO, right? Therefore, what is GM? Therefore, GM is equal to, what is change in IC? GM is equal to change in IC, right? Therefore, when you differentiate this, what you get? When you differentiate alpha into change in IE divided by VBE. But what is change in ICBO with respect to VBE? With respect to VBE, your reverse saturation current is not controlled. Your reverse saturation current is controlled by temperature. Therefore, with respect to VBE, this is constant, this is 0. Therefore, this is what it is, right? Therefore, now we want to know the relation between. Therefore, if you take your BJT, if you take the BJT, this is collector and then emitter, this is base, and this is NPN transistor, right? This is NPN, therefore this is the PN junction diode. Then we know the VBE, right, and current IE, therefore this is what is your current IE. Then we know the relation between I to I, right? We know that which is nothing, IE is equal to PN junction diode, I naught into e to the power of V by eta Vt minus 1. Then after differentiation we know, right, we already derived this, di by dV is equal to I by eta Vt. This is what we got, you remember? The same thing I am using here. Therefore, what is our GM? GM is equal to alpha into, what is dou IE by dou VBE, which is nothing but di by dV for your PN junction diode, which is nothing but IE is nothing but IE divided by eta Vt. Right? Therefore, now what is this? What is this? This is nothing but alpha into IE divided by eta Vt. What is alpha into IE? IC is equal to alpha into IE plus ICBO. Therefore, this is nothing but IC minus ICBO divided by eta into Vt. But if you take typical transistor, for typical transistor, right, for a typical transistor, for a typical BJT, because your emitter is heavily doped, that's what I told, right? When emitter is heavily doped, the body part resistance or the body resistance of emitter is very less. Maybe the voltage drop in the body can be neglected, then whatever voltage you are applying externally, that will be coming to the junction, because the base width is also very small. Therefore, that enter voltage will be coming to the junction. If the enter voltage is coming to the junction or depletion region, then eta is considered as almost 1. Therefore, your eta will be almost equal to 1, and therefore what is your GM? GM you can take, which is nothing but IC minus, we can neglect it actually, ICBO divided by Vt. You can take it as, can I neglect ICBO with respect to IC? Because IC is in the order of milliampere, ICBO in the order of microampere. Therefore, this is nothing but IC divided by Vt. This is what is your GM. Therefore, if you observe clearly, where capital IC is nothing but DC bias current, DC bias current, and what is Vt? Vt is nothing but volt equivalent of temperature, which is kT by Q, which is 26 millivolt at room temperature at a T is equal to 300 Kelvin. Okay, then therefore what I want to say here is, your GM is AC parameter. This is AC parameter. Therefore, indirectly your AC parameter is depending on DC quantity. Therefore, this is what is your bias quantity, DC quantity. Therefore, your AC parameter is depending on DC quantity, and we know that, and it is depending on Vt, which is nothing but depending on temperature. Therefore, indirectly your GM is also depending on temperature, right? Similarly, H parameters, GM is nothing but HFE by HIE, they are also depending on temperature. Therefore, both are correlated. Take it, right? Therefore, to calculate your voltage gain, just to have the summary from H parameter model, right? If you take H parameter model, whatever we have taken, H parameter model, that to simplified model. If I take simplified model, the voltage gain what we got, AV is equal to minus HFE into RL divided by HIE. Then what is HFE divided by HIE? GM. Then how to get GM? GM we will find from IC by Vt. How to find IC? That is from DC collector current, which we need to calculate from this given circuit in the problem. Then we need to calculate DC current. Then we need to calculate IC by Vt. Then we need to substitute. Then we need then we will get voltage gain. For that we don't need any H parameters, right? Because always if you take from H parameter model, we need H parameters. But even the H parameters are not given, we can correlate to GM, and the GM can be calculated from DC collector current. Therefore, if you know DC collector current and the Vt ratio is GM, that GM you can substitute here, then we will get voltage gain. Majority of the problems are related to the GM only. Sometimes GM won't be given directly, that we need to calculate from DC current equation. Okay. Therefore, with this I can say the BJT AC analysis is over 100%. Okay. Take it. Then the next topic will be BJT DC analysis. Okay. You take this, then I'll start DC analysis. I think for DC analysis I need 2 to 3 sessions. Then within 2 to 3 sessions we can complete DC analysis. After completing DC analysis, then we will go for combined analysis, both DC and then AC. Then it will give you the final amplifier which practically people use to get power gain. Okay, take it. Over. Just 10 more seconds to complete. Try to make it fast. Then we'll go for DC analysis. Okay. After completing DC analysis, then we'll start workbook. Then we have multiple problems to be solved. I think most of the sessions will be used to solve the problems only, right? Yeah. See, once you understand the theory perfect, then the problem solving is very easy if you know the procedure. Okay? Yeah. Sometimes from the problems we try to understand the theory also. But here I can say 90% of the theory is over. Maybe 10% of the theory we can get by solving the problems. Okay? Hope that is clear. That is the methodology which we are following. Okay? Now the next topic, BJT. After a long time, changing the topic from chapter 2. But this much time you will not see for MOSFET AC analysis. Why? We will see that straightforward. The analysis, impedance matching, etc., voltage gain, current gain, all those things already we know what we need and then what are we getting. That's it. What we need we already know from BJT amplifiers, and what are we getting, that is what we need to calculate from MOSFET amplifiers. Now next topic, BJT DC analysis. Maybe 2 to 3 sessions will be under DC analysis from now. Okay. Now don't write anything. What is the purpose of AC analysis? The purpose of AC analysis is to find AC parameters. Right? What are they? Voltage gain, current gain, input impedance, output impedance, etc. All AC parameters. Right? Similarly, what is the purpose of DC analysis? The purpose of DC analysis is to keep the transistor in active region, and after keeping the transistor in active region with some bias voltage and bias current at the output, those are that operating point should be constant, or I can say that operating point should be stable. Everybody understood? See, in the case of AC analysis, we assumed that transistor is in active region, then we got H parameter model, but from mathematical analysis you didn't say that the H parameter model is valid only for transistor when it is in active region, but I already correlated to qualitative part that equivalent circuit whatever we got, right, that is true only when the transistor is in active region, then that is what is correlated to H parameter model. Therefore indirectly that H parameter model or small signal AC analysis whatever we did, that is valid only when the transistor is in active region. But who is taking care of keeping the transistor in active region? If transistor is in active region, then whatever analysis we did till now, the AC analysis and the calculated all AC parameters, they are valid. For example, if transistor is not in active region, whatever analysis we did, they are not correct. Right? Therefore, whose job is to make the transistor in active region? DC analysis. Okay? Write down. Under the heading, the purpose of DC analysis. Write down the first one. To keep means what are we going to do from DC analysis? To keep transistor in a required region, not only active region, that is what is called required region, but for amplifiers we need active region. Therefore in a required region, in bracket, active region for amplifiers, active region for amplifiers. That is one thing. Number two, after keeping the transistor in active region, whatever Q point we are getting, which is nothing but operating point, that should be stable. Therefore Q point to be stable. or I can say Q point stability. This is what you can take. Therefore, the purpose of DC analysis is to keep the transistor in the required region, basically active region for amplifiers. But if you want to use as a switch, we need to bias the transistor in saturation, cutoff. Therefore, depending upon the input voltage level, therefore in that case we don't want active region, we want saturation region or cutoff. Therefore, biasing or DC analysis is not only for amplifiers, the DC analysis is also for RTL inverter, TTL inverter, ECL, all different logic families, right? But here I am speaking about amplifiers because we are under BJT amplifiers. Therefore, we want active region for amplifiers, therefore to keep the transistor in active region. After keeping the transistor in active region, whatever DC operating point you set at the output, that should be stable. If that is not stable, you may see distortion, right? That is what is called Q point stability. That is what we are going to see. Therefore, the figure of merits from DC analysis are these 2 points. Remember, in the case of DC analysis, I will not bother about AC signals because the purpose of DC analysis only region of the transistor and Q point stability, the DC voltage, DC current to be stable, right? Now, if you take AC analysis, there I will not speak about DC quantities because I speak about only AC quantities. Over. Now let's see the first circuit. We have 3 circuits, right? But out of 3 circuits we use only 1 circuit. Then that is what we use, and for that we are going to use the AC analysis part. Then that is what is your combined circuit. Okay, let's complete. Therefore, what is the circuit? Let's see. Let me erase this. Now the first circuit, I will not name the circuit, I will name the circuit after explaining the limitation of the circuit. The limitation of the circuit itself is the name of the circuit. Okay, let's see how we see. Now the circuit is, just don't write, listen. We are going to take only for common emitter configuration, right? I am going to apply the DC analysis only for common emitter configuration. Okay. Now only DC quantities. Remember, this is what is your capital VBB and RB, RC, now VCC, right? This is collector, emitter, this. Okay. Now this is what is your VBE. This is VBE. The current which is what is entering into base, right? The current which is what is entering into base is IB. The current which is entering into collector is IC. And output voltage is nothing but VCE. Here the operating point Q, this is what is called operating point. This is nothing but output voltage comma output current. This is nothing but your VCE comma IC. See, I am representing with capital letters. Very important, don't confuse. When I represent with capital letters, what does it mean? DC quantities. Means they are not changing with respect to time. They are not supposed to change with respect to time. Okay. That is what it is. Not with respect to signals, they are not supposed to change. When you keep VCE, I want VCE only. When I keep IC, I want IC only. Okay. Therefore, this is what is called your operating point, right? Now your operating point should be stable. and your transistor should be in active region. Therefore, now we are biasing with VBB, RB, RC, VCC such that transistor will be in active region. Okay. Therefore, we are understanding how to keep the transistor in active region and then how to make the Q point stable. Okay. Later on, I'll explain about DC part, AC analysis part, but maybe I can correlate now a little bit, therefore you'll understand. Let us say my highest power supply, the power supply what we are using, let us say this is 10 volts. The lowest power supply, 0 volt. Okay. I am applying VBB, some 5 volt, right? And I am getting VBE, definitely greater than cut-in voltage. Then let us say I am choosing VCE, which is 5 volt, that is what is typical. That is the maximum what you can get is nothing but 10 volts. The minimum what you can get is nothing but 0 volts. But in between whatever you have, let us say that is what your VCE, let me take it as 5 volt. Therefore, I am trying to keep it at 5 volt, exactly at the midpoint of rail to rail, right? Rail value, maximum value is 10, minimum value is 0, okay? That is what you can get at the output, right? Then what is your output KVL? If you write output KVL, what is your output KVL? Output KVL, right, is nothing but what? Your VCC is equal to the drop across these two is equal to the drop across resistor plus the drop across transistor. That is nothing but IC into RC plus VCE. This is what is your output KVL, right? Therefore, now tell me, I want VCE to be equal to 5 volt. This is what is my required. Remember, you can keep anywhere, provided, because what is the reason for the active region? The reason for the requirement, active region conditions. Active region conditions. Active region conditions. I already gave it to you, right? And derived also. What are they? Your VBE should be greater than or equal to 0.7 and what? I told you, right? If VCE is greater than 0.2, then this is what is your active region. Therefore, now tell me what is your VBE? Your VBE I am applying through VBB, then definitely VBE will be greater than or equal to 0.7 because VBB is in my hand and the RB also in my hand. I am the designer, therefore I know what value of RB and then what value of VBB if I choose such that I will get VBE. Then definitely your VBE is greater than or equal to 0.7. Yes, I can keep it. Once you keep it, I can write input KVL where VBB is equal to drop across RB plus VBE. You know VBE 0.7, VBB is known to you, RB is known to you. We can calculate IB or not. Once you know IB, then can't you calculate IC? Yes, we know IC, right? Therefore, what is that IC? IC is equal to and the DC equation. Therefore, DC equation. What is DC equation? IC is equal to beta into IB plus 1 plus beta into ICBO or IC naught. This is what your DC equation. Therefore, now if I neglect it approximately, then I can say this is approximately equal to beta into IB. For the time being, you can neglect reverse saturation current. Therefore, IC is approximately equal to beta into IB. If IC is approximately equal to beta into IB, you know VBB, you know RB, then you know VBE which is 0.7, then greater than or equal to 0.7, then you can take it approximately 0.7, then you can calculate IB also. What is IB? IB is equal to VBB minus VBE divided by RB. Therefore, we know IB and you know beta, then we can calculate IC. Therefore, IC is equal to beta into IB approximately. Then you know IC and you know RC because RC is also in your hand. That is what is your DC biasing resistor, right? Then you know IC and you know RC. Then I want or choose RC such that the drop across RC will be equal to 5 volt. If the drop across RC is equal to 5 volt, then out of 10 volt, 5 volt is gone, remaining 5 volt you will get to the transistor. Therefore, whatever voltage you want at the output of the transistor, that I can get by choosing different value of RC, provided IC is known to you. If IC is known to you from input port and input to output translation through beta, then once you know IC, choose RC to get half of the voltage which is VCC by 2. In this example, I have taken VCC is equal to 10 volts. If I take VCC 5 volt, then I want drop across RC to be equal to 2.5, then I will get VCE is equal to 2.5. I hope this is clear to you, right? Here I have taken the example 10 to 0, therefore VCE is equal to 5 volt. Done? Okay. Now, when VCE is 5 volt, is it an active region? Yes, because if VCE is greater than 0.2, active region. Yes, that is an active region, right? And maybe to complete, if VCE is less than or equal to 0.2, if VCE is less than or equal to 0.2 and this is what is called saturation region, then it is not suitable for amplification. It is not suitable for amplification. This is what we need for amplification, or your BJT will be acting as an amplifier. Therefore, we need this condition. Okay. Now, if you see here, if you choose the value such that I am getting VC is equal to 5 volt, therefore strictly speaking this is 0. Minimum you can get 0, but the minimum value what you can get at the output to keep or to use it as an amplifier is nothing but 0.2 only. The output voltage VC should not go below 0.2. You can say that is the reason why I am saying it is 0.2 volt, which is close to 0. That is what you can say. Because below 0.2, less than or equal to 0.2, transistor is entering into saturation. Right? It should be more than 0.2, more than 0.2 to 10. You can choose any value in between, but it's better to choose exactly at the midpoint, because don't think from DC analysis only, we have to think from AC analysis also, because let us say if I choose my VCE, the DC voltage, instead of 5 volt, if I choose at 2, then the swing whatever you get, because we are not going to use it as it is, right? We are going to apply the AC signals. When you apply AC signals on top of DC, then you get swing on top of DC, about DC, then the swing also should not go below 0.2, should not cross 10. It should be in between power supply to 0.2. Therefore, we have to choose DC voltage such that it's better if you keep exact at the midpoint. Even though there is a AC signal which is coming above the DC voltage, we will not go below 0 and we will not go above VCC. Right? But remember, you can choose 3 also, provided if you don't use complete swing, then you have only minimum margin 3 volt here. When you have 3 volt low you can go, and then 3 volt up you can go for a sinusoidal input signal. I hope this is what is clear. Okay. Now, therefore, the first job of DC analysis is to keep the transistor in active region. Yes, by choosing RB, VBB, RC and the beta, we got to know the transistor region. Yes, we are able to keep the transistor in active region by taking VCI, by having VCE greater than 0.2, right? Done. Once you keep, and then if you choose, let us say RB is done, VBB is over, RC is done, everything is over, then you kept it and then leave it. Then whatever VCE you set, which is 5 volt, and whatever IC you got, that VCE comma IC, that should be stable. That should not change. That should not change. Whatever operating point you set, that should be stable. Okay? Is it done? Is the concept clear? I hope that is clear. Okay? Now I'll explain a little bit about this. Then you will understand the meaning of, like, I think everybody understood what is the meaning of active region. Yes, we are able to keep the active region. And then what is the meaning of stability? That part I'll explain. If Q point is not stable, what will happen? Okay? Let's see that part. Okay? Just listen. Now, maybe just for your understanding, I'm adding AC also, right? If I'm adding AC, let us say I'm applying AC signal on top of DC. I'm just explaining, but how to couple this, I'll explain this part later. Therefore, I'm adding the signal what I want to amplify, right? Let us say this is what is your source voltage. This is what your source voltage. This is the signal what I want to amplify. And this itself is the RS, let us say, for the source, AC source. Then whatever voltage you are applying the change, right? Strictly speaking, whatever we have, what is the input now? The input is nothing but on top of DC, which is VBB. Just listen, this is very important. If you understand this point, done. I'm just trying to correlate, incorporate AC also. Therefore, now tell me, I'm trying to amplify the signal. The signal, whatever you want to amplify, that you apply. Therefore, indirectly now what we applied, on top of DC, the DC VBB is giving capital IB, actually capital VBE, then that is giving capital IB, the capital IB is giving capital IC, the capital IC is giving drop across RC, and that is giving capital VCE. Fine. Now, let us say I am applying the signal what I want to amplify. Then what is happening? When this voltage is increasing, on top of DC, on top of capital VBE only, you have small VBE, the change in the voltage because of small Vs. Then, because of change in VBE, we have change in current, small IB. Because of change in IB, you have change in current, small IC. Because of change in IC, there is a change in drop across RC. But my output voltage is not across RC. My output voltage is at the transistor output. when I say my transistor output, but we know that if IB is increasing, when input is increasing, VBE is increasing, IB is increasing, but IC is increasing by large quantity because IC is equal to beta into IB. That is the AC equation. This is DC equation. What is AC equation? Small IC is equal to beta into small IB. Beta is in the order of 50. 50 times of the change in IB is nothing but your change in IC. Therefore, more current. Then the more current you are passing through RC, more change in voltage across RC. But that is increasing. But the more change, it will be decreasing. That is what is your, let us say, this is what is your signal, what you get at the output. And we have seen this because this is kind of common emitter configuration. There is a phase shift. If input is increasing, your output will decrease. That's why we got minus sign. That's why we got minus sign. That is what is called inversion. Okay. Now, for example, if you choose, let us say this is what is case 1. This is what is operating point 1, Q1. Now let us say operating point 2. Let us say maximum I can get is 10 volts, and then minimum I can get 0.2 volt or 0 volt, approximately 0. Let us say I am choosing my VCG. I am choosing my VCG is equal to some 2 volt. I am choosing my VCG DC voltage 2 volt. How can you choose VCG 2 volt, the operating point? Yes, I can choose because capital IC is known to me. Then I can choose different RC such that I'll get different drop across RC. Then I can get VCG whatever I want. Therefore, that is what is my DC voltage which I am getting here. That is what is 2 volt. Now let us say if I say that is what is my voltage, but I am giving the same signal here. If I give the same signal, then what you get? If you take like this, then you will get clipping. This is what is called clipping because you are trying to get this much peak to peak. The same peak to peak I am expecting for different operating point. Now the operating point VC is 2 volt. Therefore now you got clipping. To do not see clipping, what is the solution? Therefore this is not acceptable. This is not acceptable. Not acceptable. Then, but I want operating point to be at 2 volts. But without see, this is what is called distortion. This is what is distortion. This is what is distortion, right? But I don't want to see this. Okay, almost session is over. Okay, but you can resume the what? You can resume the video and then you can take the waveforms because I'm going to close the session in 2 minutes. Else you can stop now immediately. If you want, you can continue the next session also, next video. Then again the same thing will be projected. Then from their point you can take all these waveforms. Okay. Maybe before that you take it and I want to rub it, but anyway you need to write down. Therefore, after completing this only, I will draw the next one to improve without, I don't want to see any distortion, right? But I want to have the DC voltage at a 2 volts due to some reason. Then without having what to do, that part I want to explain. Okay, take it. We have 2 minutes to complete the session, but 2 minutes I think not enough to complete. First of all, you can take these active region conditions which I have given already before. Then you can take it, maybe you can stop. Okay, then no need to draw, or you can resume the video and then you can take it. Okay, but first of all, write the conditions, then you can go to the circuit, the one. Only the first circuit will take time because I am explaining the concept. Then second circuit, third circuit, it will be faster. Okay. We have 1 minute. That's fine. Anyway.